So in today's lecture, we're going to continue talking about counting. We're going to kind of finish up our counting lecture today, and we're going to talk about counting when we don't care about ordering. So if you remember last time, we had made a table, 2x2 table, and maybe it looked like this. We had, when we sample, we can care about the ordering, or we can say, oops, spelled this right. We don't care about the ordering. And so we can either have ordering matter, or let's write that more legibly, more reasonably, ordered or unordered. So those are two options when we're sampling. And the other kind of option we have is we can sample with replacement, or we can sample without replacement. And last lecture we had kind of started making this table. We had talked about 2 out of the 4 options. So if we have an ordered sample, and if we sample without replacement, the number of ways, so the table is if we sample R objects from a total of n, then if we do this where we care about the order of sample and we're not replacing items after each draw, then there are n factorial over n minus r factorial ways to do this. If we're going to sample r from n where we don't care about the order but we do replace the items after each sample, we said there are n to the r possibilities. So that's the two we covered in last lecture, and we're going to continue today, and we're going to talk about the unordered cases here. And so let's kind of look at an example. So first, I suppose we can write down which ones we're doing. We're going to do this one first today, and then we're going to do, so we're going to do without replacement first, and then we're going to do with replacement. So let's look at an example of where we're sampling without replacement and in an unordered manner. So an example might be I have a basket. So here's my picture of a basket, and it has 3 balls in it, labeled 1, 2, and 3. And I'm going to draw r is equal to 2, so a sample of r equals 2, from the total of n is equal to 3 balls. And I'm going to do this again without replacement of the balls, and don't really care about the ordering. So we could first do this where we cared about the ordering. So last time we learned how to count this if order matters. So if order matters, then how many possibilities would we have? Well, we could first get a 1 ball and then a 2 ball. We could get the 2 ball and then the 1 ball. We could get the 1 ball and then the 3 ball, or we could get the 3 and then a 1. Or we could get the 2 first, and then the 3, or the 3, and then the 2. So in total, we have 6 possibilities. And our formula told us that because n is equal to 3, r is equal to 2, and so the formula said it was n factorial over n minus r factorial. So this was 3 factorial over 3 minus 2 factorial, which is 3 factorial. And that's 6. So this is what we did last time, if the order matters. How do we count this if order doesn't matter? So if order doesn't matter, well, we don't distinguish, say, between the 1, 2, and getting a 2, then a 1, or 1, then a 3, and a 3, then a 1, or a 2, then a 3, and a 3, then a 2, right? So each of these is going to kind of collapse here. Getting a 1, then a 2, or getting a 2 and then a 1 is kind of the same thing. That's going to collapse down into the kind of unordered sample of a 1 and a 2. It's either order. And the two ordered samples of getting a 1 and then a 3, or a 3 and then a 1 will collapse down into the unordered sample of 1, 3. So either I get a 3 and 1, or I get a 1 and a 3. And finally, the 2, 3, or 3, 2 collapse down into the single unordered sample of, let's say, 2, 3. So in all, this gives us 3 possibilities if we're counting where order does not matter. And what you can see is that if I can count how many unordered samples I have, in this case 3, by counting how many ordered samples I have, and then kind of collapsing down the ordered samples into a set of unordered samples. In fact, in another way of thinking about it is that if I reverse, is that if I take an unordered sample, is that each unordered, I can't spell, each unordered sample, in this case, because we have 2 items in each unordered sample, can be used to create 2 ordered samples. For example, if I take my unordered sample, 1, 2, I can use that to create 2 ordered samples, 1, 2, or 2, then 1. And in general, if I had an unordered sample of R items, I could permute those R items in any possible way to create an ordered sample. So example is if I have a sample of R items, 2, 3, up to R, the unordered sample of those R items could be used to permute, say, maybe 2, 1, 3 to R, 3, 1, 2, etc. It could be used to create a whole bunch of ordered samples. And indeed, how many ordered samples? Well, how many permutations are there of the R items? In fact, there will be R factorial of those permutations. So in the case above here, this was 2 factorial, which is 2. But in general, if I had an unordered sample of R things, I could permute them in R factorial ways and create R factorial. I guess these should be ordered, right? So this should have been parens. But R factorial ordered samples. So there's this kind of correspondence. Either you can think of the ordered samples as collapsing down into the unordered samples, or if I take an unordered sample, I can use it to create a whole bunch of ordered samples. And so the general rule, when we're talking about sampling without replacement, is that the number of ordered samples is going to be the number of unordered samples I can make times R factorial, right? If I have unordered sample, and it has a length of R, I can permute it in R factorial ways to get R factorial different ordered samples. So if I wanted to count how many ordered samples I could make when sampling, all I need to do is count the unordered samples and multiply by R factorial. Of course, what we know is that from the previous lecture is that when I'm sampling, this is without replacement. If the number of unordered samples I can make is n factorial over n minus R factorial, and that is then the number of unordered times R factorial, or I could rearrange all this and say that the number of unordered samples is equal to n factorial over n minus R factorial divided by r factorial. And so I've basically done the proof here. So if we want to, well, we can write the theorem, right? So what's the theorem? The theorem here is that if I sample r items from a total of n, and I'm going to sample without replacement and without ordering, that is, I don't care about the order of the samples, then this can be done. That is, we can create n factorial over n minus r factorial times r factorial ways. So that's the theorem. And so that will fill in kind of the spot in our table, the third spot in our table. And the proof, again, just to go through it real quick, is that if there's a correspondence, kind of an r factorial correspondence between the ordered samples and the unordered samples. The number of ordered samples is going to be r factorial times the number of unordered samples. I know how to count the number of ordered samples, and so I just divide through by r factorial. The reason for that r factorial relationship is that each unordered sample can be permuted in r factorial ways to create the r factorial different ordered samples. So this is going to work out when I'm sampling without replacement. Now, there's some notation here. This fraction, n factorial over n minus r factorial, is typically denoted n over r with brackets around it, or parens around it. And this notation, n over r with parens around it, is called a binomial coefficient. And the reason it's called the binomial coefficient is it shows up as coefficients if you expand out x plus y to the n. The coefficients are going to be in some relation to these to n factorial over n minus r factorial, and you can look up, I'll just, as a reference, not particularly important for this course, see the binomial theorem. Actually, we will talk about the binomial theorem maybe halfway through this course, but so binomial theorem is when it comes up. They're called binomial coefficients. Doesn't really matter. It's a formula. It's n factorial over n minus r factorial, r factorial. And this is read, this notation here, is read as, quote, n choose r. So the idea is I'm going to choose a sample of r. I'm going to choose r from n. And I don't care about ordering, and I'm going to do it without replacement. So it's like I reach into a bag of things, and I choose, if I reach into a bag of 5 and I choose 3, how many possibilities can I come up with? Well, it's 5, choose 3. I choose 3 from 5. And so it's read as n choose r. Okay. Let's look at some examples. Example. I have 10 professors, probably 2 F's in that. How many co-equal committees of size 4 can I create? So I have 10 professors from which I can choose. I'm going to choose 4 of them to be on my committee. So if you say it like that, it gives kind of the answer away. The answer is that I can do this in 10 choose 4 ways, right? You can think of it as sampling 10 professors, sampling R is equal to 4 from the n is equal to 10 professors. I don't care about the order of them because they're co-equal. So this is read as unordered. Don't care who's first, who's last. And I can't sample with replacement. You won't have you can't have doppelgangers of professors surfing. So this falls right into our little formula. I can do this in 10 choose 4 ways. That is 10 factorial, 10 minus 4 factorial, 4 factorial. So that's 10 factorial over 6 factorial, 4 factorial. I can write 10 factorial as 10 by 9 by 8 by 7 by 6 factorial over 6 factorial, 4 factorial. 6 factorials cancel. And that leaves me 10 by 9 by 8 by 7 over 4 factorial. And let's see, can I expand this more? That's 10 by 9 by 8 by 7 over 4 by 3 by 2 by 1. What cancels here? The 4 and the 2 cancel with the 8, and the 3 cancels with the 9, which leaves a 3. So that's 10 by 3 by 7, which that's easy to see is 210. So I can do this sampling, this committee making in 210 ways. Okay. So let's look at another example. Okay. Here's a kind of classic card problem. How many 5-card poker hands, doesn't really matter if it's poker or not, but 5-card hands can I possibly get? So here we can think about this. Think of this as choosing 5 cards. So R is equal to 5 cards. That's our sample size from a total of n is equal to 52 cards. The poker hands here, I don't care about the ordering. And without replacement. That is, I can't get the ace of spades twice, unless you're cheating. So the number of ways I can do this is, according to our formula, 52 choose 5. 52 factorial over 5 factorial, 52 minus 5 factorial. That's a big number. And that we're not going to be able to simplify. You can plug it in Google. It's about 2.5 million. That's a lot of potential poker hands. Okay, another example. Let's do an actual probability example rather than just purely counting. So let's say I have a jar with a yellow, blue, orange, and green marble. So here's my jar, and I have a yellow marble, blue marble, an orange marble, and a green marble. And the question is, if I choose without replacement from this jar 3 marbles and I could say at random, so that we can kind of assume with all choices being equally likely, what is the probability I have a yellow and blue in my selection. Right? So I'm going to choose 3 out of this. I'm going to reach my hand in, grab 3 of them. What's the probability that the yellow and the blue are among the 3? Okay, this is like a real classic probability problem. So if everything's equally likely, then what I need to do is define my event E, and probability V is the number of things in E over the number of things in S. So let's think about what E is. Or first, let's think about what S is. That's probably the easier place to start. So S is the all 3 samples from 4 without replacement or ordering. So, example, we could write this as like yellow, blue, orange is a possibility, blue, green, orange is a possibility, dot, dot, dot. I don't particularly care about the ordering them, so yellow, blue, orange is the same as orange, blue, yellow. Our formula tells us that the number of ways to do this, so this is one that would be real hard to enumerate by hand. Take some time. I have what? If I go back up to my problem, I have R is equal to 3, and I have an N is equal to 4, given that I have 1, 2, 3, 4 marbles. And so my formula says that the number of total possible ways to choose that is N choose R, or 4 choose 3, which is 4 factorial over 3 factorial. Let's write it this way. 4 factorial over 4 minus 3 factorial, 3 factorial. And you can do some math there. That should be 4. Why? Because it's 4 factorial over 1 factorial, which is 1, 3 factorial. So it's 4 by 3 factorial over 3 factorial. Those cancel. Just left with 4. So I guess maybe it isn't that much to enumerate. I was thinking of a harder problem. All right, we could actually write these all out, right? Yellow, blue, orange, blue, green, orange, green, blue, yellow. What's the last one? Yellow, blue, orange. Man, I didn't write these out in the easy would do this. Yellow, yellow. Let's say there's probably another one with a yellow. Yellow, orange, blue. Yellow, orange, green. That's going to be the last one, right? Yeah. So there are 4 of them. We know there are 4 of them, so we can stop. We know that has to be all of them. Okay, and what is our event E in this case? E is that the sample contains yellow and blue. All right, that's what we wrote up here. We want a yellow and we want a blue. So let's look at that. What are the ones that contain a yellow and a blue? Well, it's yellow, blue, orange, or it's yellow, blue, green. All right, so there are 2 possibilities there. So obviously E has size 2. Hence, the probability of this is 2/4 or 1/2. Okay, so that's some examples of sampling where we care. We don't care about the ordering, and we're going to sample without replacement. So if we go back up to our table way up at the top here, that fills in the third of the 4th of these, and that leaves 1 of them left. which is we want to sample, or we don't care about the ordering, and we are going to sample with replacement. Okay, so let's look at how to do that. Okay, here we go. So last case. Sampling with replacement and without ordering. Okay, so let's think about an example here. Example. The temptation is to do what we did last time, which is to say that the number of ordered samples should be equal to the number of unordered times r factorial. So that's what we did in the last case when we were sampling without replacement. That worked out well. We were able to derive a formula from it. Temptation is to do that. Not going to work this time. Wrong. So consider the following. If I have a basket with 3 items, 1, 2, and 3, what are my ordered samples? And we kind of did this last time, so let's go through it real quick. 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2, right? And we said that there were 6 of them. Oh, wait, well, let's back up here. We want to do this with replacement, so it's going to be slightly different. So I can get the same thing twice. So ordered, I could have 1, 1. I could have 1, 2. I could have 2, 1. I could have 1, 3. I could have 3, 1. Okay. I could have 2, 2. I could have 2, 3. Or 3, 2. And what am I missing here? So 1, 2, 2, 1, 1, 3, 3, 1, 3, 2, 1, 2. Yep, that seems like all of them. So in this case, oh, I guess I'm missing 3, 3, right? That's what we're missing. 3, 3. Okay, so this is now going to be all of them. We're going to claim that that's all of them. How do we know that this should be all of them, right? Our formula last time, so how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So there are 9 total. Is that all of them? How do I know that's 9? Well, our formula says that we're sampling 2. So here, n is 3, r is 2. Let's write that there. Our formula from last time said what? Said that the number of ways to do this was n to the r, which is, of course, 3 squared is 9. Okay, so that works out. There are 9 possibilities if I were to sample with replacement here, and I care about ordering. What about unordered? What are the possible unordered samples? Well, let's see. I could still get 1, 1. I could sample 1 twice, right? We're allowed to sample 1 twice because we're sampling with replacement. What else can I get? I could get 1, 2. So that kind of takes care of 1, 1. 1, 2, or 2, 1 gives me an unordered sample, 1, 2. 1, 3, or 3, 1 gives me the kind of unordered sample, 1, 3. 2, 2 is a possibility, 2, 2. 2, 3, and 3, 2 give me the unordered sample, 2 and 3, and 3, 3 is the last. So how many do I have here? 1, 2, 3, 4, 5, 6. So is it true that I can just multiply by r factorial, meaning 2 factorial, which is 2. No, it's not true in this case. It's not true if I take the unordered samples and I multiply by 2 factorial, I get the ordered samples. Because 6 by 2 ain't 9. So what's going on here? So consider, before we said if I took an unordered sample, I could create r factorial ordered samples. So that will work if I take an unordered sample like 1, 2. I can create 2, 1, and I can create 1, 2. So r factorial, 2 factorial, I can create 2 samples. But if I take a sample like 1, 1, I actually can only create a sample like an ordered sample 1, 1. I can't switch it. It doesn't make any sense. Like 1, 1 or 1, 1. There aren't 2 ordered samples corresponding to the unordered sample 1, 1. So this rule where we multiply by r factorial up here doesn't work in this case. And it doesn't work because we're sampling with replacement. And last time we were sampling without replacement. So we got a conundrum here. If we want to arrive at the correct way to count how many ways we can sample with replacement without ordering, well, we're kind of stuck here. We got to come up with a different approach. So here's the different approach. So let's talk about what I'm going to call the game of not thrones but partitioning. Game of partitioning. So here's an example of my game of partitioning. I'm going to have n is equal to 5 and r is equal to 2. And the question I'm going to ask is how many ways can I partition 2 objects using n minus, so r is equal to 2 objects using n minus 1 is equal to 4 walls. So let's draw a picture. I have 2 objects. Denote them as circles, and I'm going to partition them. I'm going to put walls between my objects. So how many ways could I do this? Well, I could put a wall here. I could put a wall here. I have 4 possible total walls. I could put a wall here, but I could also put another wall there, right? So now my objects, my circles, are kind of partitioned from each other. They have walls between some of them. So that's one thing I could do. Another option, so let's call this option 1. Let's say option 2. 2 objects, I could put 1 here, and 2 there. It's another way I can put walls between my objects. What's another option? Option 3. 2 objects, what else can I do? I could put 1, 2 here, and 1, 2 here. Okay. What the heck does this have to do with counting? It turns out these kind of partitions can create bins, and there's a one-to-one correspondence between, I can't spell it clearly, between this these partitions, I'm going to call them, and samples with replacement and without ordering. And it goes as follows. I can think of these walls as creating bins. So it creates a bin here, a bin between these two, a bin between these two, a bin between these two, and a bin here. And same here, there's a bin here, there's a bin here, there's a bin here, there's a bin between those two, and there's a bin there. So these walls kind of create bins as follows. And I can look at how many objects would end up if they kind of fell down into these bins here. So in this case, I would have 0 let's use green. Let's add 0 objects in this bin, 1 object here, 1 object. Oops, don't have an object there. 0 objects there, 1 object falls in that bin, and 1 object falls in that bin. In the second one, 0 here, 1 falls here, 1 falls here, 0 falls here, 0 falls there. Oh, this should be a 0, sorry. 0, 0, 2 fall in this big bin, 0, 0. And if I were to number my bins and look, then give me a collection of how many are in bin, the first bin, how many are in the second bin. 0 in the first bin, 1 in the second bin, so I'm going to put a 2, 0 in the third bin, 1 in the fourth bin, so that's 4, 0 in the last one. So there is a unordered sample, like an unordered sample of size, here we said R was 2 from n is equal to 5, right? Okay, let's look at the second one. How does this partitioning kind of live in a one-to-one correspondence with an unordered sample of size 2 from 5? I'll go through the game again. 0 things in the first bin, so no 1s in my sample. 1 thing in my second bin, so I have a 2. 1 thing in my third bin, so I have a 3. And then nothing in the fourth and fifth bin, so my sample is 2, 3. Okay. Let's look at this next one. 0 things in my first bin, so no 1s. 0 things in my second bin, no 2s. 2 things in my third bin, so my sample is 3, 3. And 0 in the fourth and fifth bin, so I have no 4s or 5s. So here I have 3 samples. They are unordered. They're of size 2, and they are sampling with replacement. Let's say with replacement from 5. So I can get a sample like 2, 4. I can get a sample like 2, 3. I can get a sample 3, 3. Right? We're replacing things, and so 3, 3 is allowable. Okay. So the argument, what I'm going to argue here, is that the number of samples of size R from n without ordering and with replacement, that because for each of these kind of partitions I can draw, I can corresponds to a sample size R from n without ordering, without replacement. This is going to be equal to the number of partitions I can draw using R objects and n-1 walls. And so this is kind of a classic thing to do in mathematics. I don't know how to count the thing up here. How do I count this? I'm going to argue how to count the second one, and because they're equal, I can figure out the answer to my first one by counting the second one. So that's basically going to be the game we're going to play. Okay, so let's do this in the kind of the full version. I have R objects and n-1 walls. My claim is that if I can count how many ways I can partition the R objects using n-1 walls, that is going to tell me how many of these possible samples I can draw. So the first thing to note is that in total, I have R plus n-1 objects, things, let's call them. R objects, n-1 walls, R plus n-1 things. And each, quote, partition of the R objects is a permutation of these R plus n-1 things, right? So here's possible partition. A bunch of walls, some objects, walls, objects, walls, objects, you know. There's some ordering. My partition, which I'm kind of drawing as vertical slashes and O's is some partition, some permutation of our objects and n-1 walls. Is that to draw one of these things, I just take all these things and I permute them around. So another possibility, another permutation is, I can move this one over here, so that is that. Something like that. That's another option. One, here's another option, option 2. And each of these things kind of encodes. So these kind of encode a R sample from n without replacement. Oh, sorry, with replacement, without ordering. And the way that you do that is you draw these little baskets under them, and then you count how many things fall into the baskets. So those are my baskets, and so I have 0 in the first one, 0 in the second one, 0 in the third one, 2 in the fourth one. So my sample have 2 4s. 2 in the fifth one, so my sample have 2 5s. 0 in the sixth one, 1 in the seventh one, so I'll have a 7. 1 in the eighth one, so I'd have an 8, and 0 in the ninth one. And so that would be my sample. Well, in this case, it looks like 1, 2, 3, 4, 5, 6, 7, 8. So I have n is 9, and 1, 2, 3, 4, 5, 6. R is 6. And that's a sample of 1, 2, 3, 4, 5, 6 of size 6 with replacement, without ordering, from the numbers 1 to 9. And so you can play that same kind of game. And so the question is, so if each of these partitions corresponds to the sample in kind of this one-to-one way, and each partition is basically just a permutation of these R plus n-1 objects, how many partitions can I draw? Well, if I have R plus n-1 objects, surely I can permute them in R plus n-1 ways. But each of these permutations is not really unique, right? So here's a particular permutation of objects. But notice that I could switch these two bars, these two walls, and I get the same kind of ordered sample, or unordered sample. So I could switch any two of the walls, and I get the same partition, as it were, or objects with each other. Because I could also say, I could take this object and I could switch it with that object. It doesn't change the partition because they're interchangeable objects. And so it encodes the same ordered sample. So I must divide through by how many of those things, how many ways that I can do that. Divide by, well, if I can permute around the walls with each other as much as I want, so I can do that n-1 factorial ways. And I can permute these objects around in as many ways as I want. And there are R of them, so I could permute them around in R ways. So I've got to divide through by n-1 factorial and times R factorial. Because that tells me how many ways I can permute around the walls or the objects. So the answer I'm going to get is, well, it should be R plus n-1 factorial, but those are not all unique permutations, so I can divide through by kind of the permutations just the walls, which is n-1, and the permutations just the objects, which is R-1. And so my answer at the end of the day is R plus n-1 factorial over n-1 factorial R factorial. Turns out this can be written as binomial coefficient as R plus n-1, choose R. And that's the answer. Because each of these partitions here encodes a particular sample where I don't care about ordering and I can sample with replacement. Counting how many ways I can play that partitioning game tells me how many ways I can draw those samples. So let's write down the theorem. The number of ways to draw a sample of R from N without ordering, mattering, and with replacement is R plus N minus 1. Choose R. Yeah, that's the theorem. Period. You can show that this is equal to R plus N minus 1. Choose N minus 1. So I'll leave that as an exercise for you guys to think about, but it's not too hard to show that those two are equal. So you can either say it's R plus N minus 1, choose R, or R plus N minus 1, choose N minus 1. Basically, these terms and denominators, you kind of can think about it either way. Cool. So that's the theorem. That's definitely the hardest one to wrap your brain around. The proof is fairly unintuitive. So let's look at, I mean, you don't need to be able to prove it for the class. You don't need to memorize the proof. Let's look at some examples. You have to remember the result. So example, okay, I'm going to have 10 passengers on a bus route with 5 hotels. The bus driver counts how many get off at each of the hotels. So you can think of a route. Hotel 1 goes to Hotel 2, goes to Hotel 3, goes to Hotel 4, goes to Hotel 5, and let's say he restarts his route. And so what the bus driver is going to do is they're going to have some record, and the record is going to say, okay, what's my stop, or what's my hotel number, and number of people that get off there. So hotel 1, 2, 3, 4, and 5. And so maybe 0 get off at 1, 3 get off at 2, 1 get off at 3, 2 get off at 4, and 4 get off at 5. All right, does that add up? 6, 7, 10. So the 10 people, that's a possibility. There are lots of other possibilities. And so the question, which you probably read the question, is how many, whoops, let's write legibly for once, how many possible records are there? So this doesn't on its face seem like a counting problem. So we can convert to counting with replacement without ordering by noting that we can encode each of these records as a sample with replacement without ordering. How do we do that? I'm just going to basically write, let's say, of sample of R is equal to 10 from R is equal to 10 from N is equal to 5, right? So I'm going to write this as a sample of 10 from 5 with replacement without ordering by just noting that, okay, 0 people get off at 1. So there are 0 ones. There's going to be 3 2s. There's going to be 1 3. There's going to be 2 4s. And there'll be 4 5s. There you go. So now I have a sample 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a sample of R is equal to 10 from N is equal to 5. And you can convince yourself that this is a one-to-one correspondence. So for each record, I can certainly do this encoding, and giving an encoding, I can always just recreate a record. So this is kind of one-to-one correspondence there. Okay. So how many ways, my question here is, of course, how many ways could I do this? And now we have a formula. R is 10, N is 5, and so this should be R plus N minus 1, choose R, which is 10 plus 5 minus 1, choose 10, which gives us, what, 14, choose 10, and I'll leave that up to you to figure that out. It's going to be 1,001 possibilities. Cool. Okay, another example. A jar contains, probabilists love these jar problems, so you're going to have to learn to love them. Again, we're going to have a yellow, blue, orange, that's how you spell orange, and green marbles, one each. So we're going to draw a sample of size 3 with replacement. And we're going to stipulate is that all unordered samples with replacement are equally likely. We'll talk in a minute how reasonable that is to say, but I'm just going to stipulate for this problem that all unordered samples with replacement are equally likely. And the question here is, what is probability the sample contains yellow and blue? Oops, let's write that legibly for you. Yellow and blue. So this is kind of similar to the previous problem. S, of course, is all such samples. And so the size of S, now if they're unordered samples with replacement, this should be R plus N minus 1, choose R. In this case, R is 3 and N is 4. So this will give us 4 plus 3 minus 1, or rather, let's write this very easily. 4 plus 3 minus 1, choose 3, which gives us 6, choose 3, which is 20. And I'll let you think about why that's true. Our event E is that the sample contains a yellow and a blue. So now we have unordered samples, and we're sampling with replacement. So I could get yellow, blue, green, or I can get yellow, blue, orange. But I could also get yellow, blue, blue, or I can get yellow, yellow, blue, and I think that's all the possibilities there are. Let's think. Seems right. Yellow, blue, could be a green or an orange, or a blue, or another yellow. So in this case, the size of E is 4, and hence the probability of E, if, as we've stipulated up here, and their stipulation is that these are all equally likely outcomes, then is size of E over the size of S, and that is 4 over 20, which is 1/5. So there you have an example of an actual probability calculation. Okay, so we've now covered the 4 different ways to sample. So let's write our table. And you won't need to memorize the proofs for all of these, but you need to know the results. So our 4 possibilities were, we could have ordered sampling, we could have unordered sampling, let's write that better, and we could have sampling with replacement or without replacement. So the first thing we said is that if we want ordered sampling without replacement, you can do that in n over n minus r factorial ways. Ordered sampling with replacement, you could do n to the r. So that was the last lecture. And then today, we said that if you want to do unordered sampling without replacement, you could do that in n factorial over n minus r factorial, n minus r factorial times r factorial. And if you want to do unordered sampling with replacement, this can be done in, how do we write this? We wrote this as r plus n minus 1 choose r ways. So those are the 4 possibilities, and it's going to be in the kind of suggested problems, in the quiz problem that I'm going to post this week. These are going to be very useful for the problems, and they'll show up on exams, definitely in the problems. Okay. So burn those into your memory. It's be good to know them. Okay. So to kind of close out today, I want to talk about a couple really useful, just practical tips for when you're solving these counting problems. And I want to point out something that won't come up kind of in a discrete mathematics course that comes up in probability. Because we all have intuitions about how probability should work. And oftentimes the problems are going to be a little bit vague about exactly how to count things. Do I care about ordering? Do I sample with replacement or not? And you're going to have to kind of figure out what the best way to go about it is. And sometimes there are better intuitions than others. So let's look at this previous example real quick, right? So we have this jar, yellow, blue, orange, green, 4 marbles, so we're drawing sample size 3. Now here we looked at unordered with replacement. And if we add equally likely samples, we got a probability of 1/5. We did a similar problem though. Let's go back up to when we talked about without replacement. Here we go, same problem, but now we're sampling without replacement. And so we sample without replacement. If we say that samples without replacement are equally likely, we get an answer of 1/2. So that's a very different answer. And so one of the questions when solving the homework is which one of those would be the correct way to solve that problem. If I didn't tell you to sample with or without replacement, and which one of those we should take as equally likely, the question is which one's the reasonable. So the point of this counting, in this class, is to give you some concrete examples for calculating probabilities. It's also kind of a very classic thing to do in probability. It's not something we're going to harp on too much. There are other more important concepts in probability. There are real probability concepts rather than discrete math concepts. But the point of counting is this. If I have a sample space, S, with equally likely outcomes, then if I want to calculate the probability of some event, all I have to do is count how many outcomes are in my event and divide it by how many possible outcomes are in my sample space. So here S is denoting my sample space. And so the point of counting is that I'm going to need to count E. Let's write this better. And I'm going to need to count S. I need to count the number of things in E, count the number of things in S. And so we went over some of the basic counting techniques and basic formula in these past two lectures. I'm going to write this in red here. The important, let's even emphasize this, the most important fact here is that we assume all outcomes are equally likely. Oops, write this correctly. We assume all outcomes are equally likely. This formula does not hold unless all outcomes are equally likely. So when you're solving a problem, so this is a little abstract now, when you go and try to solve some of the problems, it becomes much more concrete because you're going to often be faced with the question of, the problems are going to be a bit vague, and they're going to face you with the question of, say, ordering or not, replacement or not. So you'll often have to think about, okay, here's the problem. Do I care about ordering or don't I? Do I care about replacement or don't I? The important thing to keep in mind when you're doing this kind of modeling is that, however, so oftentimes you have kind of ways of choosing which one of these you work with. You need to respect the previous fact. Whatever you choose in how to model the problem, whether you make S, the order of the things in S matter, or the order of things in E matter, or you're sampling with replacement or without replacement, always have to keep in mind that in order for it to be true, the things in S have to be equally likely. So if you've come up with a scheme for counting S, but that scheme does not imply that the things in S are equally likely, you cannot apply this formula. And this is the formula that's going to be applied on these problems. So whatever the S is you come up with, it better always have equally likely outcomes. Otherwise, your answer is going to be wrong. And so when you're thinking about, okay, which one of these is the correct way to do it? Should I do it with replacement or without replacement? Well, which one of those gives you a sample space with equally likely outcomes? Should I do it with ordering or should I not do it with ordering? Well, which one of those gives you a sampling space with equally likely outcomes? Sometimes it doesn't matter the choice, but sometimes you will get very different answers. And as we saw in these two examples, you either get 1/5 or you get 1/2, depending exactly what you're assuming the base, the sample space is with equally likely outcomes. Now, in those two examples, it's kind of a modeling choice of the person solving the problem. And I stipulated that the outcomes are equally likely specifically for this reason. In reality, when you're kind of modeling, there are going to be modeling choices, and you could either model, okay, the ordered or the unordered outcomes are equally likely. It's not necessarily true that each modeling choice will be the best and will give kind of the intuitive answer to the problem that we think should be true. So let's just, in the last couple minutes of this lecture here, let's talk about some intuition. And this is going to play into next week's lectures, where we talk about conditional probability independence. So the reason I'm going to talk a little bit about this term independence, which we'll formally define next week. But it turns out that the correct way often to model these problems is going to depend on what's kind of independent. So let's concretely look at an example. So here's an example. I flip a coin twice. What is the probability of getting a heads on one and a tails on the other? So one's going to be heads and one's going to be a tail. So this is a classic kind of problem. The reason I'm really emphasizing this is going to help you on homework. So you're going to listen to this, without having done the problems, it's gonna be a bit vague. You're gonna go sit down and try to do the homework, and then you should come back and think about what I'm saying here, because it's gonna help with the homework. This is just straight up practical advice, nothing theoretical, right? So here's a kind of classic problem. Flip a coin twice. What's the probability of getting heads and tails? So this could appear in the homework. It's a little too easy for the homework, but it could totally appear in the homework. So there are a couple ways you could solve this problem. Option one, is let's do this with unordered counting. So unordered counting, I'm going to say that the order of my flips doesn't matter. So the order of heads / tails doesn't matter. So the order of my coin flips, don't really care which I do first. So one way I can model the sample space is if I don't care about the order of my flips, what are the possible outcomes I can get if I flip a coin 2 times? Well, I can get heads 2 times, I can get tails 2 times, or I can get the heads and the tails, right? So there you have 3 possibilities. Now, this is one way you could model the sample space, where I have 3 options: heads, heads, tails, tails, or heads, tails. And so here, the size of my sample space is obviously 3, and this is basically, or exactly, sampling R is equal to 2 items from N is equal to 2. So my N is equal to 2 is I sample either heads or tails, and I'm going to take a sample size 2 from the set of heads, tails, and I'm going to do it without ordering, because I'm going to say I don't care about which order my heads and tails show up, and I'm doing it with replacement, right? So my set of things I'm sampling from is heads, tails. I'm going to do it with replacement, right? So I can get heads twice. So I reach into a basket. There's an H and there's a T. I can get an H in my first one, write it down, put it back, and then reach in again. I could get H again. So we're going to do this with replacement, but I don't care if I get H and then a T, or a T and then an H. And so our formula should tell us that R plus N minus 1 choose R. If our formula is correct, this should give us 3, right? It should give us the size of the sample space. Total number of ways to draw the sample. And indeed, it's 2 plus 2 minus 1 choose 2, which is 3 choose 2, which indeed is 3. Okay, so everything works out. What's E in this case? E is I get a heads and a tails. So in this scheme, it's HT, right, which is heads, tails, or tails, heads. Doesn't really matter which order. And so by the scheme I've come up with here, the size of E is 1, if I'm counting in this way. And hence the probability of E is 1 over 3, or 1/3. I'm going to go out on a limb and say this seems wrong. That doesn't seem right. Seems like there's a simpler way of doing this. And what's the simpler way? The simpler way is that let's just write another argument, is that if I want to get a heads and a tails. So I could either get a heads and then a tails, or tails and then a heads. And if on my first coin flip I have half a probability of getting heads, and on my second one I have half a probability of getting tails. Alternatively, I have half a probability of getting tails on the first and half a probability of getting heads on the first. Now, there's this idea of independence. And this is the idea that things don't affect each other. we're going to formally define this next week. But I'm going to bring it up real quick here to say, if I flip a coin once and I get a result, I feel like the second flip is independent. What I get in the second, almost everyone would model this as independent. So if I flip the coin a second time, I would say that the probability of heads or tails in the second flip does not depend, is independent of the probability of getting the heads or tails on the first flip. And the rule, which is beyond the scope of this week, but next week we're going to see, is that the rule says that if two things are independent, say getting heads on the first and the tails on the second, and just say that the probability of getting heads on the first doesn't affect the probability of getting tails on the second. If that's true, I can just multiply my probabilities. Now we're going to formally define that next week. But, so one way of thinking about it is, okay, half probability of getting heads on the first, half on the tails, and so I should have a fourth 1/4 probability of getting heads, tails. And similarly, I should have 1/4 probability of getting tails and then heads, because I got half of getting tails the first time, half getting heads on the second time. And these are disjoint, so I should add them together. And my probability of getting tails and then heads should be 1/2. So that seems like a reasonable argument to me. But it gives me a different answer. I got 1/3 on the first time, and I got a 1/2 on this other argument. Other argument kind of involves this intuition we have, which is ultimately a modeling choice, but it's probably the better way to model a problem, which is that, well, independence, I should take a probability on the first time, and the second time, 1/2, fourth, add them together, get a 1/2, right? So I've gotten two different answers here. So what the heck's going on here? Let's look at another way of doing this. And this other way is basically going to give us the same answer as the independence argument. So the choice we made here is that we did unordered sampling. So what if we sample where we think we care about ordering? And we solve the problem that way. Okay. So in that case, what are my possibilities where I care about the order of the flips? So if I flip a coin twice, I could get a heads twice, I could get a tails twice, I could get a heads and tails, but if I care about the ordering, then that's different than a tails and a heads. So now in this way where I'm thinking about the ordering, now I have 4 possibilities. This seems to comport better with our kind of intuition about independence of flips here. And my event E in this case is that, of course, it's that I get a heads and a tails. I don't care about if I get a heads first or a tails first. So I can model that as the 2 outcomes, heads, tails, or tails, heads. And in this case, size of E is 2. And so the probability of E, 2/4 or 1/2. So in the second case where I've thought about the ordering here, where I modeled it as I care about the ordering of what's going on, I get 1/2. That comports with the case where I'm assuming the coin flips are independent, that the things I'm doing are independent. What doesn't comport with independent flips is where I've done this by thinking about it as unordered counting. This is really counterintuitive because the problem is phrased in a kind of unordered way. And so it seems like, well, I don't care if I get a heads or a tails first, I should solve this with unordered counting. The problem is that if we think about the coin flips as independent, thinking about it as ordered actually gives the correct result. I'm going to kind of put correct in scare quotes because ultimately it's a modeling choice, but probably it's really reasonable to model these coin flips as independent, in which case the ordered approach to it solves it. So the general rule that mostly works, I'm not going to say it always works, but mostly works this time kind of thing, is that if I assume my sampling it comes about from a sequence of independent actions. So in this case, you could think of it as first sampling so I'm sampling from the H and T. I'm reaching into a basket. It has an H in it. It has a T in it. I'm reaching into it. I'm going to pull it. One of them. I'm going to record it. I'm going to put it back, mix it up, and then pull another one. If I assume that my sampling comes about from a sequence of independent actions, independent meaning you don't think that the steps in the sampling should affect each other, then counting with ordering mattering typically gives the correct result. This is not, an axiom of mathematics. It's just practical advice for solving this problem. So that's typically actually going to give you the correct result. And when we talk about independence next week, we can formally kind of prove that that's true, and I can say more about that. But typically, the unordered counting is not going to give it correctly because it's basically not kind of modeling the independence. So it gives us 1/3 in this case instead of what I think most people would say as well. Its probability should be 1/2. This is not maybe always true. Maybe someone come up with an example where I'm wrong. But it's kind of a general piece of advice, is that oftentimes if you're solving it in two ways, and you can solve it in the ordered way and solve it in the unordered way, and you're not sure which is correct, and they're giving you different answers. They don't always have to give you different answers, but often they will. Think about the first directive, the prime directive here, which is that this is kind of the prime directive, is that the sampling space assumes all the outcomes are equally likely. And in order to kind of, we'll show that in order to model that correctly, when we have independent actions constituting our sampling, you want to do that where you care about the order. So the comments I'm making here may seem really abstract. When you go and try to solve the problems, you're going to run into this. Almost guarantee it. Come back and think about these comments. Come talk to me in office hours if these comments still don't make sense. But I want to head off some problems that typically arise when people get two different answers. I don't know which one's correct. Typically, the ordered one's going to be the correct one, kind of because we are assuming independence in the action, or sampling actions. I'm claiming that without proving it. Next week we can prove it when we talk about independence. I think that would be a nice thing to show that that is true. But unfortunately, the ordering of topics in the course is not perfect, and there's no perfect way to do it. Okay. The last comment I'll make is that you don't always get different answers when you solve in the ordered and unordered way. Sometimes, like in this case, you get 1/2 you solve it ordered, and 1/2 when you solve it in the or 1/3 when you solve it in the unordered. When sampling, let's say, with replacement, we have to be careful about this. And I'll say this doesn't come up as much when solving problems where you're sampling without replacement. When you're sampling without replacement, we should be more specific. We have to be careful about the ordering. That is, should the problem be solved where ordering matters or not? This doesn't come as much when you're solving problems when basically sampling without replacement. That is because without replacement, ordered / unordered are the way you count the samples for ordered and unordered are multiples, are just a r factorial multiple of each other. So I can get one from the other by either multiplying or dividing through by r factorial. And so when I calculate probability of E, here I will get either some number on the top and some number on the bottom, or I'll get r factorial by some number over r factorial by some number, and they're going to give me the same result. When we sample with replacement, we know that that's not true, as when we sample without replacement. And so being careful about the ordering is going to matter much more when you sample with replacement. And without replacement, typically these kind of issues aren't going to arise as much. Maybe not always, but typically that's how it's going to work. Okay, so that was just some practical advice at the end there about solving these problems, and it forces you to think about them. We talked a little bit about this concept of independence, which we'll formally define next week. And so next week, after we talk about independence, it'll be great to go back and think about these problems through the lens of independence. But for now, we're going to try and solve most of them just with our counting.